Welcome to the Explainer. Today, we're going straight under the hood of Python to look at one of its most fundamental processes, the call stack. It's the hidden engine that's literally powering every single function you run. You know, we write and call functions all the time, right? It's just second nature for any programmer. But have you ever stopped to think about what's really going on behind the curtain when you execute that code? Like, what is Python actually doing?
Believe it or not, a simple line of code like this one, it kicks off this whole chain reaction. Python jumps into action, starting this super organized process to handle your variables, keep track of where it is, and figure out what to do next. So, let's break that down.
All right, let's get into it. To really get the big picture, we've got to start small. We're going to look at the anatomy of just one single function call. I mean, this is the absolute building block of everything your code does.
So check this out. Every single time you call a function, Python spins up this temporary, kind of isolated workspace for it. Inside, it tucks away all the function's local variables. But, and this is the really important part, it also jots down a return address. Think of it like leaving a bookmark. It's the exact spot in the code it needs to jump back to once the function is finished. Then, once the work is done, it cleans everything up and zips right back to that bookmark.
And this little temporary workspace has a name. It's called a stack frame. The best way to picture it, really, is like a fresh manila folder for each and every function call. It holds all the paperwork, the variables, the return address, that the function needs to do its job. And when the job's over, the folder gets shredded. It's a beautifully clean and organized system.
Okay, so that makes sense for one function, right? But our programs are never that simple. We've got functions calling other functions, which call other functions. So what happens then? Well, this is where things get really interesting. Let's see how these frames start to build up into what's called the call stack.
So, to see how Python juggles all this, we're just going to trace a super simple example. Let's imagine you have a function A that calls B, and then B calls C. It's kind of like those Russian nesting dolls, right? Each one tucked neatly inside the next.
First up, our program calls function A. Instantly, Python creates a stack frame for A and puts it onto the call stack. Right now, our stack is pretty simple. It's just one frame deep.
Okay, now from inside A, we make a call to function B. So what happens? Python creates a new frame, this time for B, and stacks it right on top of A's frame. See? The stack is getting taller, and all of Python's attention is now on running the code inside B. And we go one level deeper still. Function B calls C, and yep, you guessed it, a third frame gets plopped right on top of the stack. Now C is the function at the very top. It's the active one, the one Python is working on right this second.
So once caw is all done with its work, its frame gets taken off the top. Programmers call this getting popped off the stack. And where does control go? Right back to the frame underneath it, B. Then when B is done, its frame gets popped, and we're back in A. This whole last one in, first one out thing is the absolute key. It's how Python flawlessly remembers where it is, no matter how deep you nest your function calls.
This system is super efficient, it works great, but it's not infinite. There's a limit. So it kind of begs the question, right? What happens if you just keep piling on frames and never take any off?
And that question leads us directly to the topic of recursion. A recursive function is just a function that calls itself over and over again. And every time it calls itself, what does it do? It adds a new stack frame. It's a really powerful tool for sure, but it's also the classic way to push the call stack to its breaking point. Now, to stop some runaway function from just eating up all your computer's memory and causing a massive crash, Python actually has a built-in safety net. By default, it basically says, nope, you can't go deeper than about 1,000 frames. It draws a line in the sand.
And if you try to cross that line, like if you call a factorial function with a crazy huge number, Python will just slam on the brakes. It stops everything and gives you this very specific error. And now it should make perfect sense. This isn't a bug in your code, really. It's a safety feature kicking in.
Okay, this is where it gets really cool. The call stack isn't some black box that you can never look inside. Python actually gives you the tools to peek inside it while your code is running. It's like having a programming magnifying glass to see exactly what's happening in real time. And the key to this magic is a built-in library called the inspect module.
It was literally designed for this kind of thing. They call it introspection, letting you look at the guts of your own code as it executes.
So let's circle back to our outer and inner functions, but this time, imagine we've added a little something to the inner function. We're going to use the inspect module to walk through the current stack and just print out the name of the function for every frame it finds.
And check out the output. It's a perfect snapshot of the call stack at that very moment. At the top, you see inner, which makes sense because that's the function we're in. Right below it, outer, the function that called it. And at the very bottom, you see command module, which is just the top-level script where the whole thing kicked off. We literally just printed out the exact path our program took to get here. How cool is that?
All right, so it's a neat trick. But is this just, a piece of trivia? Absolutely not. Understanding the call stack gives you practical, real-world programming superpowers. Seriously.
Just think about it. The next time you get a recursion error, you're not just staring at it confused. You know what it means. You can actually inspect the stack and see the exact chain of calls that went wrong. Or you could build these incredibly advanced logging systems that don't just tell you an error happened, but show the entire call history leading up to it. And beyond that, this knowledge is your ticket to understanding really advanced Python concepts like generators and coroutines, because they are all about manipulating these execution frames. So the big takeaway here is this huge mental shift. Before you knew this, function calls might have felt a bit like magic. Now you see it's just a clear, structured process. That recursion error isn't some frustrating mystery anymore, it's a predictable limit. And your debugging? It stops being guesswork and starts being a systematic investigation, where you can actually look at the evidence on the stack. So I'll leave you with this question. Now that you can literally see the stack, what are you going to build with that knowledge? Understanding this opens up a whole new level of control and insight. It's a huge step toward mastering your craft. Thanks for joining us for this explainer.